And the colligative properties are called such because they depend on the number of particles present, or how many particles are present, rather than the specific identity of what the particles actually are. So if you want to measure the vapor pressure for a solution, so these are all for solutions, meaning some solute has been dissolved in a liquid. I want to measure the vapor pressure of a liquid versus a solution with something dissolved in that liquid. The vapor pressure is going to be lower in solution for the solution than it would be for the actual substance. So we're going to skip over this one. I'm not going to hold you responsible for that. We're going to talk about vapor pressure qualitatively, and then we're going to talk about these two quantitatively. So we're going to use the formula for boiling point elevation and freezing point depression, and we'll just talk about vapor pressure qualitatively as we go through this section. So looking at boiling point. Boiling point is a little bit tricky because when I take a liquid and I add a solute to that liquid, if the solute is molecular and it doesn't form really strong attractions, when I add that solute, maybe it's a solid but then it dissolves, if the new solute doesn't form very strong attractions with the liquid molecules, it's not really going to necessarily elevate the boiling point. It might actually lower the boiling point. Because if the solute doesn't form strong attractions to the liquid, then these liquid molecules don't require much heat to cause them to break whatever London forces or hydrogen bonds attractions they might have with the solute, and the liquid can escape and become part of gas. So this section is not focusing on that. Okay, this section, in this colligative property section, we're focusing only on solutes that are not volatile. Did I spell that right? Is it volatile or volatile? I always mix up this A with an I sometimes. My brain cannot figure that one out. But if they're not volatile, that means they don't evaporate. And they don't evaporate because they're capable of forming strong attraction. So if you add a solute that will dissolve, it's not evaporating, that means it's forming strong attractions with the liquid. So those are the ones that will cause the boiling point to be at a higher temperature when the solute is present, or it will cause boiling point elevation, which is what the graph over here is showing. So if I add a solute that does attract the liquid strongly, that liquid is going to come in here and surround it. It could be an ionic substance. It might form an ion dipole attractions. It could be like a very polar substance capable of forming strong hydrogen bonds. If that attracts the liquid, it's going to take more energy or a higher temperature to get this liquid to break those attractions and evaporate. So the temperature for boiling is higher. So if I look at 1 atmosphere, if the normal boiling point, which is where I go from solid to liquid, would occur here, at 1 atmosphere, the normal boiling, well, that would be the freezing point, solid to liquid. So I'm looking at boiling point. That would be here. The normal boiling point, would be here at a certain temperature. If the solute attracts the liquid more, it takes more energy to evaporate, so the boiling point for the solution is going to be higher. So I get what's called boiling point elevation. And that is going to be a positive value because it's going up in temperature if there's some extra attractions causing more energy needed to break up the molecules and separate them. And so here's the formula. This really is incomplete. They introduced the Van Hoff factor later, but we already talked about it, so we'll introduce it in here. So I also need the Van Hoff factor because the quantity that the boiling point will be raised by is going to depend on how many particles of solute there are. Right? The more, I erased my picture, but the more of those solute particles were in that solution, the more effectively they'll attract the liquid, and the even higher the temperature will need to be to boil that. So the boiling point is going to be raised up more and more depending on the number of solute particles, and that's going to be affected by the molarity, which is how much solute has been added in a certain amount of solvent, and I, which is the value that tells me if I add that solute, whether it will break up into multiple pieces and provide even more attractions for the solvent. So that's the formula for boiling point elevation that we're going to use. Kb is a constant. It depends on the solvent. So most of the time we'll be using water. For water, the Kb has a known value. Molality, we already talked about. That's moles of solute per kilogram of solvent. So if we have some given information, we can plug in that formula and use it. The freezing point depression is the same formula, except the K is a different value when I'm talking about freezing versus boiling. So if you're looking at the freezing point, like the example we did earlier, that also has a Van Hoff factor. But the molality is calculated the same way. The Van Hoff factor is calculated in the same way we described. We'll see more examples of that here in a minute. And we would find the Kf instead of the Kb, plug that in, and we can determine the freezing point depression. So as we said before, if I add a solute to my solution, instead of having a pure liquid, when I mix the solute in, the particles will break up, they'll mix around with the liquid. That makes it harder for the liquid molecules to organize into a solid. So I have to cool it down even more than normal to get them moving slow enough to actually come together and form that organized structure. So the normal boiling point is raised to the new boiling point, a higher temperature, by adding a non-volatile solute. But the freezing point is lowered. The normal freezing point will be here. It's going to be lowered, so I get a lower freezing point necessary to cause something to organize and freeze when I've got these solute particles causing disorganization. It's the same type of formula. So unless I give you delta T, M, and I can't expect you to know Kb. I would have to give you delta T, M, and I. Then I could ask you to calculate Kb if I wanted to do that. But usually Kb is known for a solvent, so you just look it up. So that would probably be given to you, so I'd probably give you Kb. I would probably give you quantities of solute and solvent, and you could use that to determine molality, because that molality is moles of solute per kilogram of solvent. So you have those quantities, you would get them into units of moles and kilograms, divide, that gives you the molality to plug in here, and we can predict I, which we'll see how to do in a minute, and so we can determine how much the freezing point or boiling point is going to be raised or lowered depending on the specifics of the situation. But again, depending on the solvent, that determines the value for Kb or the value for Kf. So let's look at an example here. So here I've got ethylene glycol. I'm going to add that to water, which is what you do when you put antifreeze in your car. The ethylene glycol is very soluble in water. The ethylene glycol has the capability of forming more hydrogen bonds than water does. So the ethylene glycol attracts the water more than the water. It's a very high boiling point, so it's not really volatile at room temperature. So this is going to mix in with the water. It's going to form stronger attractions, which is going to increase the boiling point of the water. It's also going to decrease the freezing point of the water, so I'm going to have to cool it down even more. So that's why this ethylene glycol is nice for your car, because it's both a coolant and an antifreeze. Because it lowers the freezing point, that means if it gets really cold outside, the water in your radiator won't freeze, because the ethylene glycol attracts the water molecules and keeps them from organizing into a solid crystalline arrangement. But if your engine overheats because you run your car for a long time, it also acts as a coolant because it raises the boiling point of the water so that coolant can keep circulating and absorbing heat from your engine without evaporating and boiling away. So it has a higher boiling point and a lower freezing point for both of those reasons. What about the vapor pressure? How will the addition of ethylene glycol or some other non-volatile solute, how will that affect the vapor pressure? Lowers the vapor pressure, right? Because if you've got this liquid, the vapor pressure, so if this is the surface of my liquid molecules look like this. The vapor pressure is the pressure that results when some of those liquid molecules on the surface escape their attractions and become gas, and then they float around as a gas and create collisions and cause pressure. So the vapor pressure is higher if I have more gas evaporating. It's lower if I have less gas evaporating. So if I've got this solute that's attracting the liquid, I should have less evaporating at a given temperature. So less gas evaporating, less pressure as a result of that gas, a lower vapor pressure. So that's how you would explain that conceptually in a qualitative way. So quantitatively though, if I want to actually measure the freezing point, I would use the formula. And I would plug in. So what I have here is ethylene glycol. I've got its formula, so it's C2H6O2, and I know that I have 685 grams of it, and I know how much water I have. So all of that information is necessary to calculate molality, right? Because that's going to be moles of the solute, the ethylene glycol in this case, divided by kilograms of water, which is the solvent in this case. So I'd start with the 685 grams. I would get the molar mass of this, so 2 times carbon is going to be about 24, plus 6 hydrogens is going to be about 30, and 2 oxygens another 32, so that's about 62. So I'm not worried about sig figs right now because I'm trying to save a little time. I want to make sure we get through this before we run out of time. So that's grams of ethylene glycol per mole of ethylene glycol. That gives me the unit I want on top. Now I would take the quantity of water and put that on the bottom. 2,075 grams, and that needs to be in kilograms, so I'll do the gram to kilogram relationship there. I can cancel the grams of ethylene glycol, the grams of water. It's helpful if I include the substance so I know what things actually cancel. I can't cancel grams of ethylene glycol with grams of water. They're not the same thing, right? So it's really important to include the substance I'm dealing with, so I make sure I have moles of the right substance over kilograms of the right substance. So then if I divide that, I get 685 times 10 to the third divided by 2,075 divided by 62, and I get 5.32. That's my molality. So I plug that in for molality. I would go back to the table or look for the given Kf value. Since water is my solvent, Kf is 1.86. And if I don't have any ions, and this is a non-electrolyte, which means it's not going to break up, that means for every one of these I have, I will get 1 in solution. And so the Van Hoff factor is 1. And so when I multiply that, I get a freezing point depression of 9.9 degrees. The normal freezing point for water is 0, so that would mean this would have to get down to negative 9.9 in order to freeze, which really should be negative 1 times 10 to the first because I only have 1 sig fig. So that would be the new freezing point. Boiling point elevation is basically the same formula, except instead of F, I have a B here. So there, to get delta T for the boiling point, I would do everything the same way, except I'd have KB instead of KF. And for water, KB is 0.52. So I plug that in here, and that would give me 5.52 0.52 times 0.52. 2.7, so I'd round that up to 3 degrees. That's the change in the boiling point. Water normally boils at 100, so this is going to be 103 degrees Celsius, the temperature at which it will boil. Questions about that? So as we said, the Van Hoff factor is the number of particles after it's dissolved. So for the ethylene glycol, that molecule, each unit of C2H6O2, when I dissolve that in water, that starts off as a liquid, but it could be a liquid or a solid, but if I dissolve it in water, it stays together. So for every one of these, I still have 1. That's why the Van Hoff factor was 1 in that last example. If I have an electrolyte, though, that breaks up when I put it in water and I get multiple particles, the number of those I get should be the value for I. So, for example, if I have, again, a non-electrolyte, a molecule that sticks together, when I dissolve it, it sticks together. For every one of them I put in, I get 1 out. The Van Hoff factor is 1. If I have a strong electrolyte, then I have to think about, for every one I put in, how many 1 plus 1, how many total particles do I get out? That should be my estimated value for I. So in that case it would be 2. If I have, when I balance the equation that shows that dissolving of the ions, when I balance it, if I get different coefficients, I add those coefficients together. That gives me the Van Hoff factor. Right? So because I had 2 sodiums, I get 2 of those. Because I have 1 SO4 here, I get 1 of those, and so 2 plus 1 gives me a total of 3. And so if I had equal molality of NaCl and equal molality of Na2SO4, the Na2SO4 would cause a greater boiling point elevation or freezing point depression because I get more total particles to disrupt the way that the water interacts with other water molecules. So that's the estimated Van Hoff factor. The actual Van Hoff factor will be less, smaller than or less than the estimated or predicted Van Hoff factor. And that is because of something called ion pairing. Right? So when we looked at this prediction, we predicted that for every one of these, it should break up and completely dissolve, and all the ions should go around separately. If that were true, I would be equal to exactly 2. But that isn't really what actually happens, because in solution, if I dissolve a lot of this and I've got these ions floating around, a few of the charged ions will actually stick together because they attract. Right? So this positive and negative, if they come back together, they're not coming back together in a large enough quantity to actually see a solid forming. It's just a couple of the ions here and there stick together as pairs. So we get some ion pairs. So I would be equal to 2 if all the ions stayed separated. But if a few of them stick together once in a while as pairs, that acts as only 1 unit. So for every 1 NaCl that I put in, I don't get a total of 2 total particles. I don't get a total of 1 Na and 1 Cl. A couple of these will actually stick together. So I get less than 2 particles for every 1 NaCl. So the actual Van Hoff factor will be less than the predicted value. So for sucrose, the predicted value was 1, it's exactly 1. It can't be less than 1. It's not like I can get less than 1 particle for every 1 particle I add. That doesn't make any sense. For a strong electrolyte that dissolves in water, if it's a strong acid, it should produce ions. And so I predict 2 particles produced for every 1 HCl, and the Van Hoff factor is just a little bit less than that. For the predicted value here, also 2, because I get 1 Na plus and 1 Cl minus, the Van Hoff factor is just a little less than that. Here I should get 1 Mg2 plus and 1 SO4 2 minus, so I predict the value of 2. Why is this one so much less than the predicted value? Why is the predicted value here so much off from 2, whereas the predicted value here was only slightly off from 2? Yeah, I have more charge. So when I have more charge, they're attracted more, so I get a lot more ion pairs. With a charge of +2, -2, almost half of the ions are stuck together as pairs. There's a lot of pairing because the charge of attraction is so great. So if the Mg and the SO4 separate, that's 2 particles to affect the water and affect the freezing point and boiling point of the water. But if they stick together as a pair, then when I add the MgSO4, it's only 1 particle. So the average is somewhere between 1 and 2 because a lot of them are pairing up. Same thing here, I see pairing because here I should have 1 Mg and 2 Cl-. That's a total of 3, but the Van factor is a little less than that because of the ion pairs. And again here with the predicted value of 4, I should have 1 iron 3+ and 3 Cl-. Again, I get an actual value that's less than that. I don't expect you to predict the actual value. I expect you to probably use the predicted value in your calculations, but to realize that there's some uncertainty there, so it's going to limit your sig figs to probably 1 sig fig. I might give you a measured freezing point change and the information to calculate molality, and I'll give you the Kf. I might ask you to calculate the actual value for I rather than use a predicted value for I. But you just use the formula. You just plug in whatever I give you for delta T, whatever the temperature change actually is, calculate the molality and plug that in, plug in the Kf value, and you can determine what the actual value for I is, and that's how these were actually determined. By measuring what the actual freezing point is for a solution, plugging that in with M and Kf to determine the value for I. The value for I also is affected by the concentration of solution. So if I have a more concentrated solution, that means I put more of these in solution. I got a lot of them around, they're going to start meeting up. Right? If I only have a certain amount of space and I've got a lot of ions in there, if I have more ions per unit of solvent, they're going to meet up more often, they're going to start pairing up. So I get more pairs, and the actual value deviates more from the predicted value. I get more deviation from the predicted value. If I dilute that with tons of water, and the water is keeping the ions apart more, they're not going to pair up as much, so then the actual value is very close to the predicted value. So again, it's very difficult to predict what the actual value will be because it depends on how much charge the ions have, how well they stick together, and how much water there is keeping them apart as well. So one more example of this type. Here, quinine is my solute. I'm adding that into a solution. The solvent in this case is ethanol. And I want to know the molar mass of quinine. So this is a little bit different. I'm using some freezing point information to calculate the molar mass. And this is what you will be doing in the first lab experiment if you take general chemistry 2. So here we have some relationships given. I've got the density, that's the relationship. I know that, well, I'm going to need some information from the table. So since ethanol is my solvent, I'll go back here and find this information that I would have to give you to you on the exam because we're not going to have the table on the exam. So ethanol on this table is here. Its normal freezing point is negative 117.3, and its Kf is 1.99. No way I'm going to remember that. Find something factor. Okay. And actually this isn't really important because we're not given the freezing point. We're given this we're given how much the freezing point is below that of pure ethanol. So this isn't the freezing point of the ethanol. It's 1.55 degrees below the normal freezing point. So that is delta TF. That is 1.55 degrees Celsius. That's how far it is below the normal freezing point. We will need Kf, which we got from the chart. That would be given to you. We need the molality, or in this case, we actually are solving for the molality because the molality tells us information about moles of solute, and if we want molar mass, that relates to the moles of solute. What should the value for I be? Well, it tells us that quinine is a non-electrolyte. That means the value for I should be 1. Because if it's a non-electrolyte, it shouldn't be breaking up. Every one molecule of quinine sticks together as one unit, so I have a value of 1 for I. So I can solve here for the molality. I would take 1.55 divided by 1.99, and I get molality equals 0.00779. That's moles of quinine per kilogram of ethanol, which is the solvent. That's a relationship. So if I want to know the molar mass of quinine, that is the grams of quinine per mole of quinine. It tells me I'm putting 10 grams of quinine in here, so I can put that in for my grams. I need the moles of quinine in this sample. So how many moles of quinine do I have? Well, I have 0.00779 moles of quinine per kilogram of water. In this particular example, I don't have a kilogram of, ethanol. In this particular example, I don't have a kilogram of ethanol. I have 50 milliliters of ethanol. So I put that in. Then I would use the density to go from milliliters to grams. Then I would use the 10 to the third grams per kilogram relationship. Well, what did I do here? I messed up my units. Density is grams per milliliter, and I want the grams to cancel, so I need this 10 to the third grams equals 1 kilogram. Set up like that. So now it's helpful to have all these units because I can see them canceling. I've got these kilograms, milliliters, and grams. Everything's canceling except mole. That's what I wanted there. So I take that molality, multiplied by 50, multiplied by 0.789, divide by 1,000, and I get 0.00307 moles. And so that is moles of quinine, and so grams of quinine per mole of quinine is going to give me my molar mass. I think I definitely made a mistake somewhere with my calculator. Let me just double check this real quick. Yeah, I don't know what happened here. These two zeros shouldn't be here. So that means this is actually going to be a slightly different number by a couple factors of 10. Questions about that one? So we're just using this formula here, and then the rest is just the same type of relationships and conversions that we've already been doing. Just to point out, this can also determine percent dissociation. So let's say I had a weak acid. A weak acid is one that when I put it in water, only some of the molecules, when equilibrium is reached, will have donated their H plus to the water to produce H3O plus. I can dissolve this in solution. I can measure the temperature of the freezing point. I know the molality because I know how many moles I'm adding and how much water I have. So I know this value, I know this value, I know Kf. I can solve for I. When I solve for I, what does that tell us? That tells us how many of these molecules actually break up and produce ions. So if I were 2, that would tell me that this is a 100% reaction. That means my acid is strong. If I were 1, that means it's not even acting as an acid. It's not breaking up at all. If I were 1.5, that would mean half of it's breaking up and half of it's sticking together. So I can determine how much of this acid is actually reacting with the water and how strong it is versus how weak it is by doing an experiment that I use to solve for I. So that's just another application for the freezing point depression experiment and how it tells you. Why do I care how strong an acid is and how much of it's going to break up when I put it in water? It could be really important for safety issues. If it's a really strong acid, I want to handle it appropriately and make sure that I don't get even a small droplet on. My skin could burn me pretty severely.